Well, greetings, Mr. Colazar's class. We're going to start into now our gases chapter. So we'll move in gases and liquids and solids as we're going. To start out with our gases, our sections 12.1 and chapter 13 is what we'll be covering. Gases is 12.1 and then our gas laws is chapter 13. Now, our main ideas, key objectives we're going to explain the behavior of gases using what we're going to call KMT. So we'll find out about that shortly. Looking at low density for gases, how they compress, their expansion and diffusion, effusion, and pressure. And we're going to describe how the mass affects the rate of diffusion and effusion, how gas pressure is measured and then converted between different units of pressure, and the partial pressure of gases. So to begin with, kinetic energy. All matter is constantly moving. So constantly moving, either moving in from place to place like gases, rotating around like liquids, or vibrating in fixed positions for solids. But all matter has kinetic energy, and we call kinetic energy the energy of motion. So anything that's moving, which is solids, liquids, gases, all matter has energy of motion, and we call that kinetic energy. Now we're going to use that kinetic energy to describe the kinetic molecular theory, and we're going to know that to be KMT. So we're going to hear KMT a lot. Kinetic molecular theory describes the behavior of matter in terms of its particles in motion. The model makes some assumptions about gases, about the size, the motion, and energy, and we're going to look at those assumptions now. So first off, particle size. For gases, the particles are very small. They don't experience significant attractive or repulsive forces. So as they move close to each other, let's say two are going to be coming close to each other, as they get close to each other, unless they hit each other, there's not going to be any attractive or repulsive forces. Kind of like an example might be like magnets. Magnets, when they get close, start to attract each other. If they're far away, there's no attractive forces. With gases, unless they collide directly with each other, there's no attractive or repulsive forces. It's going to be one of our assumptions. If they're far apart from each other, or they are far apart from one another, so there's lots of empty space between each gas. Now, as we look at their particle motion, they're moving constantly. And as they're moving, they're going to be moving in straight lines until they either collide with each other or the walls of a container. So as they're moving along, they're going to move until they hit a wall, and then they're going to continue moving in a straight line in another direction. If they come in contact with each other, they're going to continue moving and bounce off into opposite directions, and then continue moving straight until they bounce off a wall again or somewhere or off another particle. We're going to call these collisions elastic. It's not quite right, but we're going to make some assumptions with our model. So elastic means that no kinetic energy is lost. So when they hit each other, they keep moving in opposite directions. Kind of looked at like a game of pool. If you're playing some billiards and you break and all the pool balls start bouncing all around the table, as they bounce around the table, they slow down eventually. What our idea with gases are going to be is there's no kinetic energy lost, so they never slow down. They just keep colliding and bouncing around. Now, particle energy. Kinetic energy is going to be that particles have mass and velocity. So we have our equation, kinetic energy is equal to 1/2 mass times velocity squared, where mass and velocity are what we're going to be looking at. The mass of the particles don't change. The velocity of the particles can change. So kinetic energy is going to be determined by the average kinetic energy is going to help us determine what we call the temperature, the measure of the average kinetic energy of the particles in the sample of matter. So kinetic energy is temperature. Since we can't change the mass of the particles, it's the velocity, how fast they're going, that determines this temperature. Faster the particles are going, the more temperature we have, because it's the measure of the average kinetic energy. Now, gases have low density. They have small mass and lots of volume. There's a lot of empty space. So density, mass divided by volume. If we were to look at this, we have a small mass, large volume. So density is going to be very small. So gases, low density due to large volume with low amount of mass to them. Since they have large amount of volume between the particles, we can compress a gas to a smaller spot. This is a piston here. And a piston, like in your automobile engine, is a part that it's allowed to move up and down in a closed container. So we can actually take a gas, and if we were to apply force to it by pushing down, we could compress it into a smaller area. We still have the same number of particles, but now they're in a smaller area. So gas can be compressed, or since they continue moving in straight lines in every direction, we could expand the gases by moving the piston in an upward direction. Since gases move constant straight line, they're going to continue to move up until they hit the top of the container and bounce around. So our gases are always going to take up the amount of space that they're given. We can compress into a smaller space, or we can expand them to a larger space. Well, looking at the properties of gases, effusion is going to be one idea we have. Effusion begins with the letter E, the escape of gas through a tiny opening. So if we were to have all the gas particles on one side of a container, and then as we're going, have an empty space on the other, and poke a small little hole. Eventually, the gases are going to start getting a chance to go through that small hole and move to the new opening. So effusion would be the escape through a tiny opening. And then Graham's law we're going to get to in a second. The beginning of Graham's law says that the rate of effusion is inversely related to the molar mass. So inversely related, so more mass means slower effusion, or lighter particles effuse faster. So the faster they're moving, smaller they are, the faster that they move as they're moving around. If they're smaller, they're going to be able to escape faster. So that's why we're going to say it's an inverse rate, molar mass on the bottom, so that the smaller the mass, the faster the effusion rate. And we're going to combine that in just a second to get actually Graham's law. Alright, so our particles are escaping. There goes our closed box again. Now we can see the green particles, smaller particles, are allowed to move faster and escape quicker. The blue particles are a little bit larger. They're taking a little bit more time to escape because they're not moving as fast. So green smaller, effuse faster. Now diffusion, movement of one material through a different material. Diffusion is going to be the one that we see more often. Gases easily flow past each other because there's no significant force of attraction or repulsion between them. Particles always move from an area of high to low concentration. So an example of this might be if you were to, say, cook a chocolate cake. And as you're cooking in the oven, so you get your oven over here, as you're cooking over here, eventually the smell gets over to, say, your bedroom. So you can have those gas particles slowly moving over to somewhere else. And so more concentrated over here, eventually they're going to diffuse and move around through the entire house, and you can smell that chocolate cake burning in another, or actually not burning, but cooking in another area. Burning would be another example of diffusion also, though. So diffusion, particles starting in one area, particles that start in one area, allowed to mix and move around to spread apart evenly into another area. So they start out in high concentration, and they move from high to low concentration to evenly distribute with somebody else. So diffusion, different gases equally mixing with one another. Now, to find out about diffusion, we've got what we're going to do is combine Graham's law. And so basically we're going to compare two different gases together, gas A to gas B. And this is just a comparison equation for rate. So it's going to be the rate of the A over rate of B. Now notice on the opposite side that it's rate mass, molar mass of B from the PT over molar mass of A. So we've got our PT is needed for this. But the B matches up with the top one, and A is now on the bottom of the second half of the equation. Now this is going to be a ratio. It's going to help us determine how much faster or slower A is compared to B. First substance compared to the second. So if the ratio is less than 1, the first gas is slower, A, than B. If the ratio is greater than 1, it's faster, meaning that A is faster than B. So I was comparing first substance to second substance. So what is the ratio of diffusion rates for hydrogen and helium gas? So to begin with, we start off with A would be our first one, and B would be our second gas. So it's just always the first to the second. So when we look at that, it's the rate of A over the rate of B, and then we switch molar mass of the second on top, molar mass of the first on the bottom. So using your periodic table, we can find the molar mass of helium, 4.00, H2 diatomic, so 1.01 times 1, or times 2 is 2.02. Square root of that says 1.41. So in the end, it's saying that hydrogen, H2, is 1.41 times faster for diffusion than helium. So that would be a way to say or look at the smaller the gas, the faster it diffuses. So hydrogen would actually be our fastest diffusing gas since it's the smallest. Now the second one's a little bit trickier as we're going. It's going to look for us to find an unknown gas. If neon diffuses a rate of 3 moles per second and an unknown gas diffuses a rate of 2.5 moles per, or 55 moles per second, what is the molar mass of the unknown gas? So we're going to try to predict the unknown gases, unknown gas. So this time around, what we're going to have is we've got the rate of A and the rate of B. So we know we've got 3 moles and 3 moles, and what we're going to try to do is find the molar mass of B. So we have the rate of A per second over the rate of B is equal to the square root of the molar mass of B, so B, over, and our molar mass of A, neon, molar mass of neon, about 20.18, and that, remember, is from the PT. So now we need to solve for the molar mass of B. To do that, to get the square root away, we must square both sides. So our first step is, as we're squaring both sides, to get the square root away, we now have 3 times 2.55 squared. So we have about 1.3, I guess we could say we'd have 1.18 squared is equal to the molar mass of B over 20.18. If we were to square that, we get about 1.38 over the molar mass of B over 20.8 times this side by the 20.8 and times this side by the 20.8 to get molar mass of B, and it comes out, if we multiply those two, that we get approximately about 27.9 molar mass, which is grams per mole of a substance. Now, if we were to look at that number, we're trying to find out what gas that would fit in. And 27.9, significantly looking, if we were to look in our periodic table, that nitrogen, N2, would fit about that bill. So we could find out how fast the unknown gas to predict what it actually is. From here we're going to move on to pressure next, but we'll let you stop here for now. As we're going forward, we'll continue in with gases.